Any longer, so all right guys, so just catching up. So we're going to focus primarily on weather today. So in a few days, I just checked today and the link's still not up and working, so Nikki and I are going to work with Bob Woodinger from JSA, and we'll get a link out to everyone. How many people, anyone go to the YouTube site yet? Okay. You got the email, the link to the YouTube site? Okay. So there is a video out there that's basically 2 years ago test where I explained every question and the answer to it. I was going to go through that in class, but I don't think I'm going to, because the intent was originally to do that tonight, but we just didn't get through all the content. And next week's going to be Cedar Point, and I think it's going to be another night like tonight where there's low attendance. So this will probably be the last organized class we have. I'll get you guys some stuff to go through online, including I'm going to shoot a video that's designed to replicate the advanced test. So you can kind of do that in concert. And if anybody wants to get together and do a one-on-one session, I'm happy to do that. Okay. So we're going to talk about weather tonight, and we got a couple videos in it as well.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
Makes sense? So that's really important to understand the Coriolis effect, because that is, if you think about the macro things that drive weather on the Earth, that is one of the two major drivers that drives the weather on the Earth, is the concept of the Coriolis effect. I don't think I have it in this video. I had it once. Has anyone ever seen the video of the two guys on a teeter-totter shooting a basketball towards the center? You ever seen that video? I tried to pull it up because it kind of puts it. Look for it online. You go to YouTube and put teeter-totter or basketball Coriolis. It'll pull up this video that basically shows how when the teeter-totter or merry-go-round, it looks like a teeter-totter. It spins like this. When it's still, the guys can shoot and they can put the basket, shoot it in the basket in the middle, or they can pass it back and forth to each other. But as soon as they're spinning, like if we were spinning around each other, if this was a merry-go-round we're on, and I tried to pass the basketball to you, right, it would veer because of the movement, right? And so, you know, are we stationary right now? No. You know about how fast we're moving? It's like 1,100 miles an hour around the axis of the Earth. So we basically, so this is the Earth, and this is the axis, right? So the Earth rotates like this once every 24 hours, right? And the circumference of the Earth is about 28,000 miles. So we're doing about 28,000 miles per 24 hours, which is about like 1.1 thousand miles per hour. Is how fast we are moving right now. And that doesn't take into account how fast we're moving in the solar system around the sun, which is actually even faster. I forget the number, that one's easy to calculate, right? It's even faster, it's like 24,000 miles an hour. We're going this, but we feel stationary because it's relative, right? And so that concept of the Coriolis effect is one of the two important things that we need to remember to understand what drives weather on Earth. Any questions on that one? Round of applause for first place contestant number 2. Thank you. Meeting 420, very nice day, Grayson. We started, and I'm recording this, Jake, just so you know. Okay, here's the second
animation.
important
We're going
concept.
to look at global wind patterns and talk about the reasons why the air circulates the way it does, and also patterns of rising and sinking air and how that relates to precipitation. The engine that drives it all, I guess you could say, is the intense heating by the sun that occurs only in the equator areas where the sun is shining at a very high angle of incidence. And this hot air near the equator, being less dense, rises upward. It rises upward and it moves toward the poles, and then it gradually sinks at about 30 degrees north and south latitude. So we create these big spinning circles of air that we call the Hadley cells. Now, near the equator where the air is rising, it loses its ability to hold moisture, and you get a band of high rainfall and low pressure because there's air leaving the equator. Where the air sinks, in these belts at around 30 degrees north and south, you get high pressure sinking air, which creates areas of clear skies and desert climates. Now, as this air circulates and tries to flow back toward the equator along the surface of the Earth, or as some of it heads toward the North Pole or toward the South Pole, the Coriolis effect, the spin of the Earth, causes it to bend and turn, and it's going to create the two big wind belts that prevail on our Earth, 2 out of 3. The trade winds, northeast trade winds and southeast trade winds, and then the prevailing westerlies. Now these winds curve, and the way they do because of the Coriolis effect, the winds curve to the right of their path, north of the equator. They curve to the left of their path, south of the equator, and they end up flowing from east to west or from west to east. Now the other big factor is what's happening at the poles. At the poles, the air is cold, and the cold air wants to sink. And as that cold polar air sinks, it heads toward the equator and it bumps into this air heading toward the pole here and toward the south pole here. And it creates an area of rising air, and again, rising air produces high precipitation belts at about 60 degrees north and about 60 degrees south latitude. At the poles themselves, the precipitation is quite modest because the air is sinking, and that creates low precipitation.
Okay. So, you now understand the two things that drive every weather pattern on Earth. And everything that's going to be important for you to know in navigation. Again, remember this chapter's about, how do you get there safely? And there's a whole section of questions on weather in the tests. And all of it ties back to, if you can understand these two concepts, I think it will really help you understand not only how to be a better sailor and more about why the wind does what it does, but also serve as the foundation. So, the two things that we just talked about, first was Coriolis, right? Effect, I think that's right. I think it's right. And what was the second thing that they just described here? Say again?
The winds.
What about the winds?
They call it system.
What are the two major, what's the major driver of all of the macro winds on Earth? Spin of the Earth causes the Coriolis effect.
Is it heat?
Heat, right? You can call this, heat or heat cooling, or it's typically referred to as thermal differentiation is the word that meteorologists will use to talk about. Hello, Maddie. We'll use to talk about heating and cooling, right? So everything that they just talked about here is driven by hottest places, the equator, hot air rises or falls? Hot air rises. So it rises, and as it rises, it cools off, warmer air comes in below it, that creates this, the Coriolis effect, then it turns it, which creates the trade winds and the west winds. And we'll talk about how this works on a micro level here in Long Island Sound as well, because just like this works on a macro level, it's also the thing that works on a micro level as well. So, Coriolis effect, in the northern hemisphere, winds tend to turn to the right or left of their path.
Right.
And in the southern hemisphere, they turn to the right or left of their path. Left. Low pressure systems in the northern hemisphere turn which way?
North.
The northern hemisphere. Counterclockwise. Low pressure systems in the southern hemisphere turn clockwise. By the way, what is a hurricane called in the southern hemisphere? Typhoon. What's another word that you hear them referred to as? Not as common, but typhoon would be. Tropical storm is below hurricane level.
What's it called?
Cyclone?
Cyclone is what they're called in the northern hemisphere. Anticyclones. You hear them called that in the southern hemisphere.
Give me the first letter.
Huh? Anti.
First letter.
Of what?
What it's called.
Anticyclone.
Anticyclone?
Yeah. 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 Typically typhoon stuff. Actually, I think this is important. I'm not sure if I have this later or not, so if I do, how fast does the wind have to be blowing for it to be a hurricane?
7 degrees.
Knots or miles an hour?
Miles an hour.
Okay, miles per hour. And how many?
73. Is that?
74.
Oh, I was one off.
I'm pretty sure it's 74. 74 is a hurricane. 74, I have to look them up. So I think 74 to 90 sustained, so that doesn't include gusts, is a category 1 hurricane.
How do they draw that line? Just 74?
Yeah.
Just straight up?
I don't know. Yeah, it probably goes, I'm not exactly sure where those came up with. So I don't want to go through this because I'm not sure I'm going to quote you the numbers right, and I might have it here someplace. But so so if it's calm, maybe it's a little windy, what's the first kind of like advisory or warning that you'll see? What's that called?
A wind advisory. Small craft advisory.
Small craft advisory. What's above a small craft advisory?
Large craft. Medium?
Well, sure.
Small vessel.
True, but as you think about, so what flag goes up for a small craft advisory?
Red triangle.
A red triangle. Okay. What's 2 red triangles mean?
Thunder advisory.
Gale. Next is storm. What do you put up for a storm? Ben, you should know this. What do you put up for a storm?
Oh, the hurricane sign? Yeah, the red dot.
And what do you put up for a hurricane?
2 of them.
2 of those. So, and I should know the numbers, but I don't. I think I have them in here someplace later. If not, I'll email it to you because I do think that's on the test. Okay, let's see what I got next. So, this is an animation. It's a loop of 20 years of winds in the northern hemisphere. So remember how it talked about the equator, which is down here, heats, right? And it falls back down. The air heats and it falls back down. This is about this line right here. Whoop, let me cycle in again. So here you can see the wind coming up off, falling into the pole, and it falls into the pole, it bends, right? It comes and butts up against this and rises. That's what creates the westerly. What is this wind here called? Do you know?
Jet stream.
The jet stream, right? So this is a 20-year view of what the jet stream looks like. So the important thing for us is the jet stream is the thing that is the major driver of the macro weather patterns, right? So if you go back to that previous image, right, about here's the equator, the tropic, right? So you have the wind going up like this, so you got this big circle being created. You have this big circle being created, right? And this, the range of the westerlies in here, as this is the wind that's coming off the poles, right? So the sinking on the poles and going, bending to the right. As that mixes, that's what creates the jet stream that flows around our part of the planet. Okay? So jet stream is, I think that is a test question to know what what the name of the breeze is. And typically that wind is up and around the 25, 30, 35, 40,000 foot range. How long does it take to fly to San Francisco? Anybody know? What's up, Jen, a question?
Will the jet stream, you know how the jet streams usually on the upper half of the United States?
Mm-hmm.
Will it like ever go below or not?
Probably not below, actually we'll talk about that in a second.
Okay.
Got it. You might know how long it takes to fly to San Francisco?
5 hours. 6 hours there and like 5 hours back. It depends on what the wind is.
Yeah. Depends on what the jet stream is. That's why it takes longer to fly there, because you're no matter how you get to San Francisco from here, you're going to fight some headwind, and you're going to have some tailwind coming back, right? And so that's why you have that. So this is actually, Jenna, to your question, this is an interesting. So this is a view of the velocity of the jet stream. So here's North America. Here's us up here. This is December, January, February, and this is June, July, and August. So you can see that the jet stream, where we are as we tilt away from the sun in the wintertime, is actually a lot stronger than when we're tilted towards, like we are right now, the sun in the summertime. So you have those steering patterns. In the wintertime, the jet stream typically dips down further to the south. You know, does it ever dip below the United States? Probably not. But you do sometimes get these big knuckles that drop down. I sailed one time down in the Bahamas in, it was February that I was down there, and you almost never get cold fronts down that far, but a cold front had gone through in the southern Bahamas, and it was like 45 or 50. And so the jet stream had dipped far enough south that cold front was able to come all the way through behind it. So, very unusual. But the jet stream basically is the thing that is the dividing point between warm temperatures and cold temperatures. Colder temperatures being north of the jet stream, warmer temperatures being further south. When you then have these major systems, like a low pressure system, it doesn't have to be, this is not a hurricane, it's just a typical low pressure system. They typically follow, they're steered by the path of the jet stream. Jenna?
So obviously it obviously seems to have to do where the earth is compared to the sun, but can the jet stream affect how I know it can affect how warm and cold it is in certain seasons, but since it's more predominant in the winter, is that playing into what affects?
Yeah, well, so I think the better way to say it is that because the tilt of the earth changes, it changes where the jet stream lies, and therefore that's what changes how far north and south weather patterns go, right? So in the wintertime, so this low that I just had tracked through here, if that was a really strong low, that would be called a nor'easter, because it goes south of us and it has breeze come in from the northeast, and that's why it's cold, on the back of a nor'easter. Typically in the summertime, when the jet stream, so now we're tilted towards, it's not as strong and it's shifted further north, right? That's why the warmer temperatures go further north, and a low pressure system that was steered by that would typically go along the jet stream well north of us, up here, so that the impact from a low pressure system and a cold front associated with it's not nearly as dramatic for us. So, you've ever seen these two images on a weather map? What does this one designate?
Low pressure system.
Low pressure system's here, so that's always marked with an L. What's this? Cold front. What's this? Warm front. Basically what this means, if you think about it, it makes sense, right? Because what direction does breeze go around a low pressure system in the northern hemisphere?
Counterclockwise.
Counterclockwise, so this whole thing is spinning like this. So therefore, this warm front is moving up like this. So there's cooler temperatures in front of it and warmer temperatures behind it. This is a cold front, so what's behind it? Colder temperatures, and in front of it is warmer temperatures. So we're going to look at in a minute. This is exactly where we are right now. This will help the guys do on Largemont Race Week in a second. Let's talk about a cold front.
This animation is a way to describe how precipitation happens at what are called cold fronts and warm fronts. These are weather systems that develop wherever masses of cold air collide with masses of warm air. And the name actually comes from war, where armies would meet along a battle line called a front. And one way to think about the difference between cold fronts and warm fronts is to think about which mass of air is going to win the battle. So we'll start with a cold front. This is a situation that happens where cold air moves in like a big wedge underneath warm air. Cold air is always heavier than warm air, and so it's denser, and it's going to tend to slide under the warm air and push the warm air upward. Anytime you have air rising upward, it's going to expand and cool and lose its ability to hold moisture, and this will give you a band of clouds and precipitation along the cold front. On weather maps, if you watch the weather on the news, you can see cold fronts marked by lines of blue teeth that point in the direction the cold air is moving. Along cold fronts, you typically have very intense local thunderstorms and rainstorms, so it might pour rain for a short time, but then quickly, usually within an hour or so, the front will have moved on. So a cold front is where the cold air pushes underneath the warm air, and you have high rainfall and usually intense thunderstorms. Now, the warm front has in common a couple of things with the cold front. One is that the warm air still goes up on top of the cold air, but in this case, the warm air is actually pushing the cold air out of the picture. So the warm air is winning, and that's how you can remember it. It's a warm front. The warm air pushes against the cold air, squeezing it out. Like imagine squeezing a watermelon seed between your fingers. It kind of squeezes out, right? And as the air pushes, it also rises up over the cold air. Rising air, again, loses its ability to hold moisture, and you tend to get clouds and rain. Along warm fronts, you typically have more mild, more mellow, more spread out rainstorms rather than really local intense thunderstorms. And if you're looking at the weather on the news, they mark warm fronts on maps with red half moons that point in the direction that the warm air is pushing the cold air. So that's cold fronts and warm fronts, major precipitation belts in many places on the earth.
434, 47, and this is 47, 7. And this is 74.
Okay, so that was warm and cold fronts. Make sense? We're going to talk about cloud types, but there's unfortunately a bunch of questions on the test related to cloud types. And so we're going to have a whole section on that, but this shows the 3 or 4 different types of clouds that you get associated with a warm front. Any questions on the cold and warm front? Okay.
A squall line is, simply put, a line of storms. Squall lines can also be called multi-cell linear storms, but the most common term used to identify these storms is squall line. A squall line consists of storms situated along the gust front at the leading edge of the line. The gust front acts as the system's updraft as air is lifted upwards along the leading edge of the line, even as colder air rushes out and away from the storm's course. Lines of storms can persist for hours and even days as they move east or south. A line of storms will see its biggest severe weather threats along and just behind the gust front. The main severe weather threat from squall lines is damaging winds, but large hail and even weak tornadoes are possible. Another threat is significant flash flooding, especially in situations where the line itself is moving slowly as individual cells move over the same areas repeatedly. Linear systems are easy to track and predict, as they typically follow a pretty straight path. Lines of storms can be incredibly damaging, and thus you should always pay special attention when one is approaching your area.
Start and restop the camera, and I know you guys are going to have to go on.